Good afternoon. My name is Ludwig, and welcome to Learning with Unstructured Data. Today we are only going to do the lectures, so the tutorial part starts next week only. And this will just be an introduction, overview of the course, the objectives, and how things are going to work. So I'm going to present the course, talk a bit about the evolution of artificial intelligence and machine learning, and then unstructured data and how deep learning is related to unstructured data in the first hour. Then we'll have a short break, and I'll carry on in the second hour. So these 2 hours will be 2 blocks of 1 hour each, so we can rest the brain a bit and wake up before the next part. This course, many of you took the machine learning course. This one is different. The other one was more fundamentals and theory and so on. This one is more practical. Is a more practical course. We'll try to give you some notions of machine learning. Some people did not do the machine learning course. I'm going to do a brief overview of that, or just remind those who did. So structured versus unstructured data. We're going to focus mostly on unstructured data in this course, and deep learning. I'm going to talk about the foundations of deep neural networks, different types of neural networks, and the ways of training and optimizing and trying to adjust the models. And mostly we're going to do the practical part with TensorFlow. Probably we will also look a bit at Keras at the end, but mostly with TensorFlow in Python. So the idea here, this is for the first part of the semester, which I will be lecturing and giving you the tutorials, and then the second part will be with Professor Rui Rodrigues from the math department. And this will be mostly a practical work that we're going to do. So the first 6 weeks are going to be more theoretical and an introduction to TensorFlow with some toy examples, and then the later part of the semester, practical application. And this is reflected in the evaluation. So you're going to have one written test on April 11th. This test can be replaced by the exam. So this is a theoretical part, and it counts for 30% of the grade. 70% of the grade is practical. There is a small tutorial on this first half of the semester. This is a TensorFlow tutorial that you're going to create. So this is basically for you to show that you learned how to use the basics of TensorFlow, and you're going to write a tutorial in whatever topic that you want, with whatever data set that you want, and just to explain how to use TensorFlow and TensorBoard, and then I can give you a bit more details on what you need to cover, but this is a small assignment for you to consolidate what you learned with TensorFlow. And the theoretical part, the test will cover these theoretical notions that I'm going to give in the lectures. And the idea is that you, at the midpoint of the semester, after these 6 weeks, you are ready to start the final assignment. And this will be the second half of the semester, and that final assignment counts 50% for the grade. Okay? You have the course site here on the page for the course. You'll have this link on click to. I'm going to put there the planning for these first 6 weeks and the exercises. What is there is still last year's planning, so I'm going to change something a bit, but it can give you an idea of how things are going to run. These are the recommended bibliography that you should read or should have available. These are all available online, although I'm not going to focus on the legality of obtaining these online, but that's up to you. The software we're going to use, this one is legal and free, so we're going to use Python 3.7. I think the current version of Anaconda has 3.7. That's the easiest installation. You can install Anaconda and TensorFlow. if you use TensorFlow for the CPU, it's trivial to install. You can even install it deep. With GPU, it's also easy, but maybe you need to update the drivers. You need to install the drivers for the graphics card and so on. But at least for this first half of the semester, you don't need GPU acceleration. We are only going to use simple data sets, so it may take a few minutes to run, and you don't have to worry about it. We are probably going to use Carriage. This would be a bit just at the end of these 6 weeks. I'm saying probably because this was a last minute change and we don't have Carriage installed in the labs. So I'll just do a kind of survey in the labs of how many of you have laptops. If most of you have laptops, we'll do a bit of Carriage. If not, then we'll leave it to next year, because you cannot use this in the lab and it wouldn't make much sense. So let's start now the actual subject matter. Those of you who did the machine learning course should already know this. The basic idea here is that we are trying to create a system in the computer that can learn by itself. We can automate learning. So this is not a recent idea. So you have this quote from 1959 where there was this goal of trying to give the computers the ability to learn by themselves. And this is a more formal definition by Mitchell in 1997, that if we have some way of measuring the performance of the system in some particular task, then we can say that the system is learning if that performance increases as we give it more experience, more information, more data. So this is the idea that we're trying to, the basic idea behind machine learning is that we have a system that can improve performance in some task if we give it information. So you can see here that we already have a framework that tells us we need to define how we measure the performance, what the task is, and what counts as experience, as information. So we need to have a clear idea of those parts before we can even start to try to conceive a system that learns. So these are basically the three legs that we need for machine learning: the task to perform, a measure of performance, and the data used to improve performance. And then this, you can imagine many different tasks like identifying spam emails, identifying faces, identifying voice recognition, and so on. But also not only classifying and identifying things, but also generating. For example, generating text, generating decisions for a game, for driving an autonomous vehicle, and so on. So there are many different tasks of different types that we can specify, but as long as we can specify the task, the measure of performance, and the information that we're going to use, we can formulate a machine learning problem and then try to solve it some way. Now we can consider basically 3 plus 1 or 4, but 3 basic types of machine learning problems plus a mix of those. And one would be unsupervised learning, which is basically trying to get the system to learn how to change the information we give it into some different representation that may be more useful. A common example of this is clustering, where we want to take some data set and then decide which elements must go together and which are separated. And so we're trying to find some structure in the data. And the basic idea is that we have some values. The features are those values that describe each example. We pass it through the system that is learning, and at some point the system learns how to give us new values that help describe those examples. These may be the labels for the clusters, these may be some different representation and so on. But the difference between these kinds of machine learning problem, unsupervised learning, and this other kind of supervised learning is that for supervised learning we can actually measure some error because we have a target value that the system must achieve. So this would be an example, for example, face recognition. We have a set of labeled faces from different people, and we know that the system must recognize which person the face belongs to. And if it fails, we know that that photograph belongs to person A, but the system is saying person B. We can measure that error, and we can tell the system to correct itself, to adjust the parameters in order to make a more accurate prediction. So this is the difference between supervised and unsupervised learning. In supervised learning, we have this target label in addition to our features. In unsupervised learning, we are trying to find structure in the data. Of course, from the point of view of the system, as we're going to see some examples, this may actually look like the same thing. So this is more conceptual because of how we look at the data, what we are considering to be features and what we are considering to be something we want to predict, rather than actually in the implementation in the way the system is conceived. We can also split these problems into two sub-problems, which are regression and classification problems, depending on what we're trying to predict. With the regression problem, we are trying to adjust to some function or to some continuous value. Acho que não tens cadeira. Tentar roubar uma vida. Olha, fica comigo. So with the regression problem, we're trying to adjust our prediction to some continuous value, and we can imagine this as we're having a shape that we're trying to fit, and our system must then output that shape, that continuous function. In classification, we are trying to separate things into different classes. So this is not merely a difference between continuous and discrete values, but it's also because in classification we are trying to partition the volume or the space where our examples can be, so that this part belongs to some class, this part belongs to another. So basically, regression, we are trying to fit some things. Classification, we're trying to split, to partition the volume into different parts. Both of these can be done with supervised learning because we do this with labeled data and we can measure the errors the system is making. Then there is another kind of problem, reinforcement learning, which we didn't cover this last year. I'm going to try to give some examples of this year if we have time. But this is similar to supervised learning, in which we have some way of evaluating the results. However, we cannot evaluate the results at the moment each decision is made. So consider, for example, a game of chess. Our system must learn how to play and which moves to make at each turn, but we cannot tell on the first move if it's going to win or lose, if that's a good move or a bad move. So we have to find some way of crediting each move with the outcome after a certain number of moves, and we find out whether or not we lost the game or won the game. So the same thing if we're trying to teach the system to drive a car. We know things went wrong when the car collides with a tree or something like that, but maybe the mistake was done quite a few steps earlier, and we need to identify it. So this is looks like supervised learning in some sense, and can be done. There are some ways that are very similar to supervised learning, but there is this problem of assigning credit for each decision depending on the outcome that can occur later. And then there is this hybrid kind of problem where we have both unsupervised and supervised learning. This happens mostly because labeled data is more expensive than unlabeled data. For example, if you want to collect images of different kinds of birds, where each bird is identified, it's much harder than simply collecting images of any kind of bird without any label. So usually you can have a large data set of unlabeled data and a smaller data set of labeled data, and you can, with semi-supervised learning, mix in unsupervised and supervised learning techniques in order to use more data than what you would have available. So we're going to look at mostly examples of unsupervised learning and supervised learning. I'm going to try to give you a few, at least one example of reinforcement learning maybe in a few weeks, if I can fit it in somewhere. But this semi-supervised learning is basically an extension where you bring together unsupervised and supervised learning. So, fundamentally, we have an optimization problem. We have a model. A model is an expression of a class of hypotheses that we're going to explore for achieving our goals. So, for example, suppose that we want to partition the volume of points in a specific way by a straight hyperplane, for example. So the possible hypotheses that we're going to consider would be all the possible hyperplanes, and the model would be a mathematical description of the hyperplane with some parameters that we could adjust. So this is what we have. We have a model. The model usually has these explicit parameters, and we're going to adjust them in order to find the right solution for the problem. And we do that by minimizing a cost function or maximizing a target function. So it's basically an optimization problem when we end up solving it. So let's look a bit at the evolution of machine learning and how machine learning is connected to artificial intelligence. So this is basically the birth of artificial intelligence, this research project on artificial intelligence that brought together many famous people, Minsky and Shannon and so on, to discuss this idea of artificial intelligence. So this, the basic assumption was that all these aspects of reasoning, intelligence, learning and so on could eventually be precisely described so that a machine could also do them. Intelligence would not be something strictly for humans, but we could also automate it in machines. But initially, the most successful aspect of artificial intelligence was dealing with explicit rules. So things like logic programming and theorem demonstrations and things like that, expert systems and so on. So this is an example of an expert system which is based on rules. These rules are specified by the programmers, the people who develop the system, and they give a formal roadmap, let's say, a formal recipe for how to reason about something. So we have this MindSim program in 1975, which was used for the identification of disease or different types of bacteria and so on. And it had a set of rules like this. If the stain is gram-positive and the morphology is coccus and the growth conformation is in chains, then there's a 70% probability that is streptococcus and so on. So these rules were not automatically generated. They were inputs and created by the programmers. But then what the computer would do would be to follow all the rules and reach the correct place in the tree to give this prediction. So this was initially very successful, but it kind of hits a wall at some point because it's very hard to specify rules for a lot of things. For some things it's relatively easy. For other things, for example, like image recognition or things like that, we cannot tell what the rules would be to distinguish between a person and a car, or a dog and a wolf, or something like that. So all those problems where we cannot specify the rules would require a different approach. And this was also in the beginning, a very promising approach with neurons and the perceptron, which had a specific update algorithm for reducing iteratively the error in classification. And so this model of the neuron and the Rosenblatt perceptron were initially seen as something amazing because we could avoid having to give all the rules and the system would learn. However, after some analysis, this turned out to be equivalent to general linear models that were already used in statistics, and people knew that these were very limited in what we could apply them. So basically, we need to find some features to describe our data, and then we have a linear classification. We choose a linear hyperplane to divide the the region where our data is and decide these are class A, these are class B. And since we are only using a straight line to separate the two, this is very limited, and it turned out that the neuron was the same as these linear classifiers. So actually we can even see the equivalence between logistic regression and the neuron. So to remind most of you of this, or for those for whom this is news, logistic regression, we assume that there is some function that can give us the probability of each example belonging to class 1. Let's suppose we have only two classes, class 1 and class 2, and there is some function that we could approximate that would tell us the probability of belonging to class 1. We want to separate the classes on a hyperplane where the probability of belonging to one class is the same as that of belonging to the other. So this would be the frontier. For one side it would be one class, the other side the other class. So one way of doing this, we can approximate this probability function with this logistic function, because it varies from 0 to 1, so it's a convenient function to approximate the probability. It's also continuous, the derivative is continuous, so all those things are convenient. And when we do this, we can find that the hyperplane that cuts between the two classes, so that region where it would be equally probable to belong to each class, can be specified by this vector here, by a perpendicular vector, and we can use then this cost function, the logistic loss, as an error function, and as we minimize this, we can find this line. So this we can use to separate the two classes. The thing is that if we have a neuron model, so this is basically the basic element of a neural network, is a neuron, which receives as inputs values that are multiplied by different weights, so these are parameters that can be adjusted. And then we have an activation function here that is not linear and gives us the output. If we use as an activation function the logistic function, which is also commonly used for neurons, this ends up being exactly the same model as the logistic regression. So neurons seemed like a great idea at first, but then when people looked at them in more detail, they were the same thing as was being used in statistics for decades. There is some slight difference in the way this is trained. So the way the function is, the loss function is minimized in logistic regression is usually different from what we do in neural networks, but the model is the same. So the power to represent and to correctly classify examples is the same. So this was a bit of a disappointment, given all the hype and all the promise that was attributed to the neuron model and the perceptron. And so when this was found out that were basically linear classifiers, people got disappointed. Actually, it was theoretically possible to go beyond this by connecting many different neurons. However, there was no way of training, of fitting the model then, because the algorithm for the Rosenblatt perceptron works with one neuron, but if we chain many of them together, then the algorithm would not work. So this led us to this AI winter, where on one hand all those expert systems already reached quickly a dead end, because we could not really, if we could specify all the rules, then things tend up to be so simple that we don't need much the computer for much. At least this was the feeling back then. And in particular, artificial neural networks got a bit stuck because of this problem. There were some developments in the logic programming, for example, and artificial intelligence developed more in that area, but it was mostly academic research. It was not so much used as today. Machine learning is used everywhere in the industry. However, in the 70s, there was this idea of backpropagating the error through layers of the network. We're going to look at this in more detail next week, but this started to appear, and then in 1986, it was shown how we could use this to train networks or chains of neurons with different layers, and this could be used for much more powerful problems, or would be a much more powerful classifier than a single neuron or those linear classifiers. In parallel with this, there was also development on other methods, for example, the kernel tree for support vector machines, which also allowed for those non-linear transformations, and this really started to give a boost to machine learning, because now we were not limited to linear classification, to separating linearly separable classes, but we could start with the features that we chose. This would still have to be done by humans to select the adequate features, but then we could do a non-linear transformation, and when we finally do the linear classification, we are looking at the problem in a different shape. So now we could try to separate classes much better than just with the original linear classifier. And also, in the late 90s, there were some experiments for multi-layer networks and also convolution networks. We're going to look at convolution neural networks in more detail in a few weeks. But at the same time, some benchmarks and data sets started to appear. So if you start to have some standard data sets, then it's easier for people to compare different algorithms, and it started to give a boost to the development of these algorithms. Another thing that happened was ways of training neural networks with many layers. This started in 2007 with the idea of pre-training layers independently. So if we have many layers, we have a problem of trying to backpropagate the error, which is something I'm just talking about now in an overview, but we're going to focus on this. So this is basically things that we're going to focus during these weeks. But there was this notion that we could short-circuit the process by first pre-training each layer independently and then stacking them together and just give a final fine-tune to the whole thing. Eventually, this ended up not being necessary because of this rectified linear unit, which has a basic property of not saturating the derivative, so the derivative does not tend to zero, and this speeds up a lot the training of the network, along with some algorithms for training for adjusting the weights that also improve the speed. And finally, the hardware. So these general purpose graphics processing units really gave a boost to neural networks, because now we could do lots of calculations in parallels with thousands of processors, and this made things a lot faster. Not only the general purpose GPUs, which many people can use in graphic cards, but also specific processor units like the TPU from Google or the Nirvana from Intel, which are specifically designed for dealing with neural networks. So this is for training neural networks, and we're starting to have hardware that is built just for that. So this is what makes deep learning so powerful today, all this combination of different techniques and hardware. And the biggest difference now is that what we're doing is we're stacking nonlinear transformations, all these layers of the network. Even though each layer can be used as a linear classifier only, the output of the neurons is not linear relative to the input. So what comes out is not a linear transformation of the input. And as we stack these nonlinear transformations, we can look for different aspects, different parts of the structure of our data. And so we can actually do away with this pesky first part of choosing the right features. So for most machine learning, most of the time we spend in machine learning, in classical machine learning, is trying to find the best features to describe our data so that the classifiers or the learning algorithms can work properly and give good results. With deep learning, we step over that part and we just add layers, and the neural network will transform everything until eventually it finds some good representation of the features. And this is an illustration at different layers for identifying images. This is for a convolution network in the first layer it focuses on features like edges with some orientations, but then in the deeper layers we find things like circles or actually eyes or legs or faces or things like that the network is trying to identify at different layers. So these nonlinear transformations result in different representations of the data that eventually give us the best representation for classification. And this no longer needs to be done by humans. The network learns the different representations. So I'm going to give here a very simple example. This is the exclusive OR. We have here false and false gives false. True and true is false too, because the exclusive OR only one of them can be true. And if true or false and true, this gives true. So the blues are the true ones, the red are the false ones. This cannot be separated with a linear classifier because there is no line here that can successfully separate the true ones from the false ones. But if we add a hidden layer on our network with two neurons, each neuron is doing a different transformation of the data, and this is the output of neuron 1, the output of neuron 2. So neuron 1 is putting one of the true ones here, the two falses, and then the true one, the other true one on this side. And the other neuron is doing this slightly differently, which means that the third neuron on the output of the network can split the data this way and correctly classify. So this is the idea of these nonlinear transformations that give us different representations of the data. We can look at what's going on inside the network. So this representation seems a bit strange, but I'm showing you this one because this is easy to do with tensor boards, and we're going to do this kind of things. So what I'm showing here is the inputs. These are the two input values. So false, false for one example, false, true for another, true, false, and true, true. So black is 0, is false, white is true, is 1. These are the target labels. So false, false is false, false, true is true, and so on. This column here are the target labels, and this is what the network is doing. These are the responses of the two hidden layers, and this is the response of the output of the two neurons on the hidden layer, and this is the response on the output. So you see the response on the output is correct for all examples. The first one is false, the second one is true, the third one is true, and so on. But what happens here is that those that are false, the neurons are answering with different values. And those that are true, the neurons are answering with the same value. So they are separating the points in that representation. I can show another example a bit more elaborate. So here we have the data, this red class here and the blue class here, and we want to separate the two. This is also something we cannot separate with the linear separation because of the shape. These are the two neurons on the first hidden layer. So they receive the XY coordinates from the data and they output these values. So they are transforming the data into this shape. Then we have two other neurons on the next layer. They receive the output from these two and output different values. And then we have a final neuron. I put on the X value just the ordering of the points, so point 1, point 2, and so forth. And we have here the output of the neuron for each point. And you can see that we have almost all the red ones there. There are a few here. And almost all the blues down here. There are a few that we cannot separate, but it separates most of the points, just this one neuron. But the reason this one neuron can separate them is because they are already projected into this transformation here, where the blue ones are almost all here in this corner, and the red ones are spread out over there. And this, in turn, is possible because it starts from that transformation on the first hidden layer. So you see, as we stack these layers, we can create different representations until we can get the right classification at the end. But this is an example of supervised learning. We know which are the red, which are the blue. We can measure the error here, and we can tell the system to optimize by minimizing the error at the output. We can do this without having these labels. And an example for this, for unsupervised learning, is an autoencoder. The idea is that we have input data. We have here a hidden layer with three neurons, and we want to create in this hidden layer some different representation of the input data. Just like what we're doing here, we are creating different representations of the data. However, we don't have labels, we don't have classes, we are not trying to separate the classes. So what we can do is we create a network. In this case, we have 8 inputs. Each of these rows is one example. So this would be 1, 0, 0, 0 for the 8 inputs. This is 0, 1, 0, and so on. These are the data that we have. These 8 inputs are fed into each of the 3 neurons in the hidden layer. So each of the neurons has different weights. They can respond to different inputs. But then in the output layer, we also have 8 neurons, and what we are forcing the network to do is to make the output equal to the input. So we don't have any additional labels, we don't have classes, but we have the features from the input, and we are telling the network that the output must be equal to the input. This is how the network looks in the beginning. So after a few iterations, this is the output. It doesn't look at all like the input, so the network still hasn't learned. But if we carry on training the network, eventually it does this. So in this case, the network is always outputting exactly the same as it receives as the input. So this is unsupervised learning in the sense that we don't have labels for our data, we just have the features. But note that from the perspective of the system, of the network, it makes no difference. It's always trying to optimize some measure of performance, so minimizing this error, and that's what making the network train. But the interesting part is not obtaining the same as input. That would be useless, we already have it. It's what happens inside the network, which is in this hidden layer, in these 3 neurons. As you can see, to recreate the input correctly, in these 3 neurons we have different combinations of on and off for each of the 8 values. So this one is 1, 0, 1, this is 0, 0, 1, this is 0, 1, 0, and so on. And we have all the 8 combinations of 2 values represented in the hidden layers. So we are creating a re-encoding of the original values just by forcing the network to output the same as the input and then looking at what's happening inside. So let's see another example of this. Those of you who did machine learning, you probably remember the first assignment in which you had a description of fake and true and real banknotes. And this was 4 dimensions, so each banknote was described by the average and standard deviation and the entropy and so on of the images of the banknote. So each banknote was described by 4 continuous values. One thing we can do to project this 4-dimensional data into 2 dimensions is to use principal component analysis. This finds the directions where the variance is greatest and allows us to do this projection by preserving as much variance as possible. And this is what you can see here. These are, one of the colors is the fake notes, the other is the blue. Actually, the data set just makes this distinction, but doesn't tell us which are the fake and which are the true ones. But you can see here, red and blue, and you can see there is a very large overlap in this region. So if we are just projecting by maximizing the variance that remains, this does not really separate the two or does not really follow the structure of the data. So one thing we can do, what I did here was to create an autoencoder that inputs this the original 4-dimensional data into 6 neurons. Then these 6 neurons feed another layer with 4, then another layer with 2, then we go back again, 4, 6, and then the output has 4 neurons to reproduce the original data. And now we train the network exactly as we did here to force the output to be the same as the input. But what we really care about is what happens in that middle layer of two neurons. Because now those two neurons, the activation of those two neurons, are a bottleneck in the representation of the data, and that one only has two dimensions because of those two neurons. And if we represent the data in the activation of the two neurons, we have this data here. And as you can see, it's much better separated between the two classes. So actually, we force the network to learn a nonlinear transformation of the data that now better reflects the structure of the data, and we can even see the two classes separated here, even though we did not give the classes to the network. So the network was only looking at the features, at the coordinates of the points, and not the classes themselves. So this is one example of a use for autoencoders and deep networks, which is to create a good representation for some purpose, even if we are not doing it with labeled data or we are not considering the labels. This, by the way, is a representation of the network on tensor boards, and I'm not going to detail this right now, but this is some of the tools that we're going to use, and you can look at the graph like this.
One question. If we didn't have the labels, how do we know that the autoencoder did a good job?
Because the autoencoder, each point here is described by a vector of 4 features. And we require that the 4 output vectors of the autoencoder have the same value as the 4 input vectors. So it's exactly the same way we're doing here. We know it's a good job because this vector is the same as this vector. We are comparing the input to the output. That's how the autoencoders work. Okay? So the labels are just used for plotting, but they are not fed into the network. So one question that we can ask at this point for machine learning and deep learning especially is where we are in this hype cycle. So usually, as we saw previously in artificial intelligence in many developments, there is some event, some trigger, somebody finds something interesting, then everyone is very enthusiastic about it. This is the biggest thing since sliced bread and it's a big revolution and so on. But then they find out that it's not really that good, and then everyone goes away and things stabilize. But eventually we get into something where at some point where things are stable and people are actually using that technology. So the question is that we don't really know where we are at each moment. We can only find out retrospectively when we look at the previous decades or something. So in a few years we'll find out if this course still has students or not. But at this point I cannot give you any assurances regarding this. Okay? But it seems promising, only the future will tell. So what has this to do with unstructured data? Because the name of the course is to deal with unstructured data, machine learning with unstructured data. And the idea is here is really on that part of how we select the features. So structured data is basically data that comes in a table. You have each column with one feature, so each row, each example is described by a set of values, and those values always have the same meaning. So one can be blood pressure, the other height, the other age, and so on, but they always mean the same. This means that you can use this data, these vectors, in machine learning or select the right features and so forth, but the vectors are all the same for all the examples, and they have the same meaning. This, of course, may depend on context, so it's not necessarily that the third element of the vector always means the same thing, but if you have the table for your hospital patients, then that column is always means that, or the banknotes and so forth, and you know what they mean. And they always have the same number of attributes, all the examples, and the same meaning for all the attributes. So this is what characterizes structured data. This is ideal for machine learning, especially for classical machine learning and for statistical analysis, because the attributes that describe each example are always in the same number, always in the same position, in the same order, and so they have a fixed match between different examples. So the first attribute of example 1 corresponds to the first attribute of example 2 and 3 and so forth. They're all the same size. We can define how many parameters we need for the model and so on. The drawback is that this takes a lot of work to prepare and maintain, because someone must be filling in those tables and keep everything organized and make sure there are no missing values or incorrect values and so forth. So examples here would be a table of seismic events and the magnitude and location, or maps of gene activities and so on, where you can specify what each value needs. Then we have semi-structured data, which you cannot really put it in a table, but it has some structure. For example, you can have XML data or JSON or something like that. There is no guarantee that the values come in the same order or they are all there, but you can extract some things because you know what is the syntax and the semantics of those records. This can also happen in technical text. So if you have, say, research papers in a specific area, there are lots. The important terms there are fixed terms, and you can probably identify them. You can have things like access logs to a server. Some events happen, some don't, but it's semi-structured. But this is, even though there is some structure to this, and we know what each element means, this is already a problem to use in machine learning, because the input size for each record can vary. Attributes are not the same across examples, so some examples may have some attributes, some others. So even when we go to semi-structured data, there is already a problem in trying to use machine learning here. And this is especially serious in unstructured data. In unstructured data, we don't have a semantic value assigned to each of the inputs. So, for example, an image, the image itself, as it can be input into some system, is a set of pixel values. But we cannot say what the third pixel on the top row means. Is that part of an eye? Is that a leg? Is that the background or something like that? That depends on the rest of the image. So there is really no way of trying to figure out the semantics of each value. We have to look at the whole thing because it lacks that structure. The same thing for free text. For example, if it's not very technical text, then everything depends on context, and you cannot really identify just based on one word what that would mean. Phone conversations, voice, video, and so forth. So there is this estimate by Merrill Lynch that 80 to 90% of useful data is unstructured data, but the use of the word estimate here just means they took the number out of their hat or something like that, because there is no way of estimating this. But certainly most of the data is unstructured. When you bring together all the videos on YouTube and things people chat about on Facebook and the images of their cats and so on, of course, in that case, if you label everything a cat, probably you get right 90% of the time, and 10% it's a baby or something like that. But most of the data is unstructured, and if we can use unstructured data, then we have access to a lot more data than with classical methods. And often within structured data, you can have unstructured data that is not used. So this is, it very often happens that you have a table which has lots of indicators, like, for example, when did the accident occur, how many people were involved, if anyone died, and then you have a comments field where people describe the accident. And actually most of the information is there, and the rest does not tell us much about the accident, but we cannot access that information because it's unstructured and we don't know how people are describing the accident. So this is difficult to use with classical machine learning because of the need to extract features. So the classical approach would be to try to convert the unstructured data into some kind of structured data, explicitly designing ways of extracting information. For example, you can go through images and measure the overall entropy of the pixel values, or try to find vertical edges or horizontal edges, or do some operation like that, and then create a table with the different values for those images, and that would be your set of structured data, your features. Things like in text mining, you can also create tables of words, try to figure out which words mean something in some context, and so on. And this can take years to perfect these techniques to extract information from unstructured data. The big advantage here in deep learning is that, in theory at least, we can step over all that process, just feed in the raw unstructured data, and hope that somewhere along the line things will get sufficiently organized for us to be able to use that data. So, with classical machine learning, especially if you have changing conditions or adversarial systems where you're trying, for example, to identify people who commit credit fraud, but they are also trying to escape your detection. So this may require fast adaptation of the system. And this step here, which must be done by humans, is a very rate-limiting step. If we can avoid that with deep learning, we can improve things a lot. So the connection here between unstructured data and deep learning is that deep learning is at least seems to be the best way so far to solve problems with unstructured data. So to sum up this first part, I just gave a brief overview of the course and the idea of how machine learning and deep learning fits in with artificial intelligence. I would recommend that you read chapters 1 and 2 of Dane's book and chapter 1 of Deep Learning by Goodfellow for this part.
No slide 29. Explica uma coisa, isto é o input, certo?
Não, isto é o PCA do input, tem 4 dimensões. É aquela coisa das notas falsas que fizemos em A, não é? Mas o input são 4 dimensões, são 4 valores. Este é o output do PCA projetado para 2. Portanto, é o PCA que são os 2 componentes principais.
Mas se nós damos isto como input...
Não, damos as 4 dimensões à nossa... Isto é só uma comparação. Não, damos os 4, fazemos o mesmo que isto, só que em vez de ser estes 8 coisas, não é? São 4 valores contínuos e à saída da rede tem de ter os mesmos valores.
Sim.
Portanto, a rede vai querer reproduzir o input no output. Mas a rede tem, esses 4 valores entram para 6 neurónios, depois para 4, 2, 4, 6, diz? Não, as 4 não. São só as fichas. Não, isto são 6 neurónios. Os 4, eu omiti o input e o output. Portanto, se quiser, temos 4 inputs e 4 neurónios de output. Mas isto é o miolo da rede, são as camadas escondidas. Okay? Portanto, há 4 valores de entrada que vão para 6 neurónios. Tal como aqui, por exemplo, tu tens 8 valores de entrada que vão para 3 neurónios.
Ok, mas não estou a entender porque é que são 6 neurónios.
Isso foi porque eu fui experimentando até dar um boneco comigo. Não é uma receita fixa, não é? Devias pôr com mais, não é? Mas isso há 4...
A única questão é o input e o output têm que corresponder.
Sim, isso são. Portanto, os 4 valores de entrada e há ali 4 neurónios de output também. Portanto, eu só estou a mostrar a parte de dentro da rede, porque o resto é fixo, depende dos inputs e do output. E aqui é assimétrico também, normalmente faz-se o autoencoding assimétrico e o que nos interessa é só aquilo. Portanto, o que se faz tipicamente é treina-se isto, depois deita-se fora esta parte e fica-se com esta rede aqui, que transforma o input de 4 dimensões neste output de 2 dimensões.
Esses 2 neurónios aí no meio vêm do conhecimento que nós temos de ter as 2 classes.
Não, isso é porque eu quero... Não é as 2 classes. É porque eu queria projetar para 2 dimensões para poder fazer o boneco. Também podias ter 4 classes, assim que não interessa, porque as classes não estão aqui. Não é? Sim. É só, da mesma maneira como eu fiz o PCA para 2 dimensões, para fazer o boneco em 2 dimensões, fiz também um autoencoder para as duas dimensões. Se tu quiseres fazer para mais, por exemplo, aqui eu fiz um autoencoder para 3, porque queria fazer os 3 bits, não é? Basicamente isto são os 8 valores codificados em 3 bits, com 0 e 1. Portanto, dá para fazer isto com 3. Isto também funciona com 2, só que depois já não tens diferenças tão grandes, não é? Tens ali uns cinzentos e assim, porque ele tem de usar os valores contínuos para conseguir fazer a distinção entre eles. Mas basicamente o que tu escolhes no meio depende do que é que queres fazer com o autoencoder, não é? Como é que queres que a representação seja.
Eu não estou matriculada nessa disciplina. Queria saber se tem problema para assistir a aula.
Não, assistir não. Mas vais te inscrever?
Então, eu não coloquei no plano de estudo que eu fiz. Eu não sei se vou conseguir mudar depois, mas
Ok.
de qualquer jeito.
Está bem, estas não há problema. Depois nos laboratórios, não sei se está espaço para tudo, mas se trouxeres o teu computador, ficas na aula. Ok. Tudo bem, sim, para mim não.
Outra pergunta. Você dá uma disciplina de informática, não?
Sim, sim.
Que é de terça ou de quarta?
Terça.
É terça, né?
Bioinformática aplicada no mestrado de bioquímica.
Eu queria fazer, mas estava tendo horário. Mas é de terça mesmo,
Sim. Terça das 9 ao meio-dia e depois das 2 da 1 às 3.
Entendi. Obrigada.
Nada.
Diga-me uma coisa, os trabalhos de conferência ainda?
Pois isso ainda não sei, porque o ano passado foram individuais, mas eram 7 alunos. Agora com 30. Os primeiros vão ser individuais, porque eu tenho tempo a avaliar e eles são pequeninos. O primeiro, o de agora é o primeiro, exato, aquele dos que vale 20%. Porque esse é fácil de avaliar e não há urgência. Agora, o outro tem o problema de que tem de estar tudo avaliado antes do exame. E o professor Luís Rodrigues vai ter que decidir ainda isso. Mas só podemos decidir depois de ver quantos inscritos é que há no final, não é?
É que já há muito pelo que eu
São
vi.
33. Eu já estava em 31, já está mais?
Eu acho que sim.
Hoje estava em 31 e acho que já há pessoas a querer se inscrever. Mas não pode ser muito mais de 30 porque o laboratório só dá para 30 e nós não temos hipótese de abrir outro turno. Portanto, não sabemos.
É tanta gente que está a ver um quarto de pessoa.
O primeiro não é muito mau, mas o segundo sim, é mais difícil, porque o segundo é muito extenso e tem de ser avaliado rápido. Portanto, o professor Luís Rodrigues vai decidir isso e se calhar vão fazer grupos de 2. Mas depois, para a segunda parte, já não será ali na página, eles partilham um drive no Google Drive, porque depois os datasets são grandes e assim, mas depois, eu vou falar com ele de qualquer maneira. Se ele já decidiu isso, eu posso vos dizer. Senão depois vocês veem com ele.
Certo.
Ok?
Obrigado. Só outra coisa. Que forma é que nós temos tipo dar à rede neuronal de unstructured? Eu tenho que dar tipo alguma informação com alguma estrutura ou não?
Não. Se tu lhe deres, nós depois vamos ver, há várias maneiras diferentes de lidar com isso, mas tu não precisas presumir a estrutura dos dados. O que tu podes fazer é dar-lhe uma imagem, dar a imagem. Agora, se tu usas uma rede neuronal que tem um número fixo de neurónios, tu tens de dar as imagens sempre do mesmo tamanho. Então podes dar, por exemplo, uma imagem grande, toda a preto, e com a tua imagem diferente lá dentro, ou fazer um rescale, ou assim. Se tu usas redes puras de convolução, em que a mesma transformação é aplicada pela imagem toda, o que tens é o output que vai depender do input. Se o input for maior, o output é maior. Mas isso normalmente é usado para fazer segmentação de imagem ou labeling específico, assim. Depois há redes que são recorrentes em que podes dar coisas sequenciais. Por exemplo, texto, não é? Vais alimentando e quanto mais texto tiveres, mais voltas a rede dá. Mas ela não se preocupa se são muitas ou se são poucas. Não é? Portanto, há diferentes formas de lidar com isso.
É que é aquela coisa de pensar como é que eu pego a imagem de um conjunto de. ou input layer. Mas em conjunto nós temos um conjunto fixo de informação. Ou seja, um conjunto fixo de informação que tem que dar alguma espécie de estrutura.
Não necessariamente, por exemplo, nas redes de convolução não é assim, porque o mesmo kernel é aplicado pela imagem toda e depois produz um feature map do resultado de aplicar o kernel na imagem toda. Portanto, tu vais transformando a imagem olhando para umas zonas para a vizinhança de cada pixel. Essa é uma forma de fazer, ou também para sinal que seja numa dimensão, portanto, faz, ou 3, até podes fazer isso conforme, podes ter redes de convolução 3D. Portanto, há maneira de fazer isso. Se forem dados sequenciais, podes também usar redes recorrentes. Enfim. Eu vou dar alguns exemplos, não em detalhe, mas só para falar do tipo de magias que dá para fazer com isto. Okay, so now this will be a bit lighter, this second part, and I'm going to start talking more specifically about deep learning. So in the first part I just gave a brief superficial overview of some ideas, mostly to give you a notion of what we're going to explore in more detail. And now let's start to look at some important concepts here for deep learning. So I'm going to talk a bit about this idea of nonlinear transformations and the difference between shallow learners and deep learners, or I'm going to focus specifically on classifiers, but this can be generalized for other types of learning. And we're going to look at the problem of overfitting. So basically adjusting our model too much to the training data, and so that it starts losing performance outside the training data. Then I'm going to give at least an attempted explanation of why deep learning is so successful now, but looking at this problem of overfitting. So we already saw some aspects, techniques and hardware, but also this overfitting problem is also relevant. And then I'm going to finish with some particular examples just to give you an idea of what we can do with this. So let's start with the nonlinear transformations, we can start by looking at what we can do with linear classification. So this would be an example where we have these two classes, blue and red. These are gene activity values and the difference between normal cells and cancer cells. And we can see that we can draw a straight line here and separate the two correctly. So this is basically what we can do with general linear classifiers. What we can do with one neuron or one layer of neurons, we can do many of these lines, but one neuron basically gives us one line of this. This can be done, for example, with logistic regression, which is a standard linear model, very used, and it can give us this kind of classification. But if we have a more complex problem, for example, like this, then we cannot really separate this with a single straight line. Okay? So basically, why can't we do that with logistic regression? What we're doing here is we're trying to adjust this function that we presume would approximate the function that gives us the probability of belonging to each class, and we decide that this function should have this sigmoidal shape depending on these vectors, which are a linear combination of the inputs. So actually, the shape, this function looks something like this. We can say that the probability of belonging to the red class is very low here, then it increases here, and then it's positive here. But since the values that we put here are just a linear transformation of the inputs, this step here will always be in a straight line. We cannot make it curved. So that's why logistic regression is just a linear classifier, and it will not work well if we have this kind of frontier in a curve. Then we try to adjust this line as best we can, but it will not classify all the points correctly. But this is because the linear classification in this representation of our data cannot separate the data correctly. Maybe we can create a different representation of our data where we can cut things straight and solve this problem. So this is the idea of the nonlinear transformation. Let's suppose that we take the coordinates of our points, they are in 2 dimensions, and we had a third dimension that is not a linear combination of the two. For example, we multiply them together, and we project this into a curved surface in 3D. So this is what we have now in 3D. We have this in a curve, and now we can solve the problem of linear classification in 3 dimensions instead of 2. It's still a straight separation, only now it's in 3 dimensions, so it's not a line, but it's a plane that cuts the two, so it's straight. But since we projected the data into a curved shape, this straight line now intersects the surface where our data is projected by a curve. So actually, if we project things back to the original space, we now have this curve here. It's still not good enough to classify these well, but if instead of just using the 2 original coordinates, we also add a third coordinate which is the product of the 2 features, this non-linear transformation allows us now to do a curve where we only have a straight line. And we can go into higher dimensions. So we can add the product, the square of the first coordinate and the square of the second one, and now we have, when we project things back into the original space, we have this curve. So in this 5-dimensional space, logistic regression is doing a straight hyperplane to separate the two. But since this transformation, when we expand into 5 dimensions, is twisting this plane into a curve, when we cut in a straight plane, we get this curved frontier here. So this is what we can do with nonlinear transformations, even with linear classifiers, by increasing the dimension of our data with these nonlinear transformations. We can go as high as we can, and as long as we do some nonlinear transformation to a sufficiently high space, we can possibly use a linear discriminant to classify our data in that higher dimension. And this is very used, especially with support vector machines. I'm not going to explain how we get here, but support vector machines basically need the inner products of the vectors of the features, the labels, and the parameters or the support vectors that we choose. So this would be vectors of 2 examples. These are coefficients, weights that we give the examples, and these are the labels. But we can do an implicit transformation into a higher dimension by using these kernel functions, which give us the result of what would be if we multiplied the transformed vectors. But usually this can be in a very simple expression, so it's easy to compute, and we can use these kernels to go even to infinite dimensions, for example, in the case of Gaussian kernels. So basically, we're doing this. We chose our features, we do this nonlinear transformation, we do the linear classification in some higher dimensional space, and we could, in theory, classify anything in this way. So this is an example of a support vector machine using a polynomial kernel. When we project it back into the original two-dimensional space, we have these curves. We can adjust the parameters of the kernel and make it curve more, curve less, whatever we want. So this is what we do with shallow classifiers in classical machine learning. If we use a linear classifier, we can only separate the classes if they are linearly separable. But if we add that nonlinear transformation, that expands the dimension of our data in a nonlinear way, then the linear classification can be used to separate things. But note that what we're doing here is we're taking all the data and expanding it into higher dimensions with some twists, some distortion, but we are not really considering if there is some better way of representing the data. That is done in this part by humans who select the features, but the nonlinear transformation is basically we put some sticks of dynamite and then everything blows and we try to solve the problem there in that space. But it's not really a very intelligent way or something that will adapt to the data. For example, if you use this kernel here, this polynomial kernel, it's the same kernel regardless of whether these are images of cats or sonograms or something like that. It doesn't matter, you just take the data in, change the number of dimensions with that transformation and do the classification. So, this, in theory, it works. So if you use, for example, Gaussian kernels in support vector machines, you could theoretically approximate any function arbitrarily, or if you use even with one hidden layer in a multi-layer perceptron, you could approximate any function arbitrarily. But the thing is that to solve more intricate classification problems, you just increase the number of dimensions blindly, and you start getting things more parameters or more flexibility in your model, which leads to problems such as overfitting and so on, as we're going to see. With deep classifiers, we don't do it like that. The idea is that even though single neurons are linear separators, so they can separate things that are linearly separable, they do a nonlinear transformation. The output is not just a linear combination of the inputs. You have a linear combination of the input, but then you have a nonlinear function for the output. And in deep networks, we can combine different layers like that, and so the transformation can be deeply nonlinear because we are doing nonlinear transformations, chains with other nonlinear transformations, and so on. But this is different than just doing a nonlinear transformation into a very high dimension, because now all these layers can learn different representations. So, for one thing, the kind of transformation that we're doing depends on the data. It's not just something we decide a priori, but something that is learned from the data as the system is optimized. And for another thing, these different transformations can actually represent different useful aspects of the data. For example, you have this example that I showed in convolution networks, where at different layers we are representing different aspects of the images in the inputs. So it's not just a matter of exploding the data into many dimensions. We are changing representations and keeping them more efficient. So we don't need to go into such an arbitrarily large space. We keep the representations more relevant to what we're doing. So this is the big difference between shallow learning and deep learning. And one of the important reasons why this is such a big difference comes from these no-free lunch theorems, which basically there are several of them depending on different conditions where we are doing the learning, and also they apply to optimization problems in general. But the idea here is that if you have a learning algorithm that performs very well on a certain class of problems, then that learning algorithm will perform poorly on problems outside that class. So there is no algorithm that will perform well in all classes of problems. If you have some kind of machine learning trick to solve a particular problem, then the cost of that is that it would work poorly on other problems. So this is one of the reasons why deep learning is so important. Since no single model can be best at all tasks, we really could use a framework where we can quickly create different models adapted to different tasks. And the idea of deep learning allows us to do that. We can use, for example, convolution networks for images. They work very well on images, but recurrent networks don't work very well on images. On the other hand, for text, recurrent networks can work well, convolution not so much, but we can change the network, the kind of architecture, and still keep the same framework, the underlying framework, for training, for tuning the models. And then there is also this problem of overfitting. So one of the things that can happen is that our model performs very well on the training set, and we get a hypothesis, an instantiation of our model that classifies the training set very well, but then we do that at the cost of poor performance outside the training set. So this is the notion of overfitting. We have adjusted too much to the data that we know, and now we are just looking at irrelevant features, and we cannot perform well outside this data. So deep neural networks solve this first problem. They make it very easy to devise new models and to adapt models to different problems. They also help a bit on the second aspect, because we don't need to explode the data into such high dimension. We can do it in layers, gradually changing the representation here. But even so, when we have a deep neural network, we have lots of parameters, so we have this overfitting problem. The basic idea is that if we don't let our model adjust too much, then we may not be able to classify our data correctly. But if we let it adjust too much to every single detail, then it's more likely that it will get things wrong when it meets new data that was not in the training set. So this is a problem which is extrapolating from the training set to outside the training set. And deep networks are very susceptible to this, because they have lots of parameters. So it's very easy to adjust too much to a small data set, and then things go wrong from there. But note that the more data we have, the less of a problem this can be. So if we have really lots and lots of points, and we have everything covered about what can probably happen for future points that we're going to meet, then it's a lot less likely that we're going to make a mistake. If we can classify our data set correctly, then it's less likely that we'll make a mistake outside. So overfitting is, this is basically the idea. We can adjust. This is the training error. We are adjusting the model to our training data. This is as we increase the power of the model, for example, the number of dimensions we explode our data into. But at some point, the performance outside the training set starts to degrade, and our error starts increasing, because we are adjusting too much to irrelevant details that don't generalize. This can happen with deep learning. This can happen with any classifier. But there are some ways of preventing overfitting, like adjusting training, checking the model, selecting the best model, and so on. But one way of reducing the problem of overfitting is having more data. The more data that we have, the less likely it is that overfitting will occur. So the more data that we have, the more powerful models we can use. The more complex the problem, the more powerful models we need to use, otherwise we cannot solve the problem. So this is really one way of understanding why deep learning is now becoming such a success. If we have, for classical machine learning, we have some kind of problems that we can solve, and we don't need much data. So classical machine learning can solve problems with fewer data points, but it gets stuck at the complexity of the problems we can solve with just shallow learning systems. Deep learning needs lots of data, because we have lots of parameters. So if we don't have much data, then it performs more poorly than classical machine learning. But if we have enough data, then the kind of problems that we can solve with deep learning are way more complicated than the kinds of problems we can solve with classical machine learning. So at some point, when we have enough data, then deep learning really starts to take off. And this is basically what happened around around 2010 or something like that. So you can see here we had this in 2006, this Caltech database of 101 classes of images, and each class had, they had from 40 to 800 images, but on average about 50 images for each class. And they had this computer vision problem of trying to identify which class each image belonged to. And the classical computer vision methods of segmenting the image and so forth could do this with about a 26% error, and there were no deep learning methods, even though at this time convolution networks and so on were already starting to be being used, but they could not beat the classical methods with this data set. But then in 2012 we had this ImageNet data set. This has 1.2 million images, 1,000 categories with many hundreds of images per category or thousands of images per category, and also general purpose GPUs. And now at this point, large convolution networks dominated the problem of classifying the images. There were no classical methods that could compete with deep learning in this case. So basically, at some point we have enough data, and now we can use these very general complex models, and they can perform adequately in this case. And you can see the dominance of deep convolution networks from this on, 2012, 13, 14, and so forth. You can see the error reducing at each year, so 15%, 13%. At some point, when we reach around 5, 6%, we are already at the error, at the level of human error. So it's hard to go beyond that because the actual labels may not be correct, because humans cannot classify the images with 0% error anyway. So this is really one of the reasons for the success of deep learning. We have lots of data, and we can now use that data to solve this kind of complex problems. Okay, so just to wrap up, I'll give a few examples. This is the AlexNet, the one that won here in 2012 and started this whole thing. This is the number of inputs of neurons, or actually this is a convolution network, so these are repeated over here. But you can see in this first block you have 150,528 values that are being output from the first layer. Then you have 250,000, then 186, and so on, until at the end you have the 1,000, which corresponds to the 1,000 classes. So you can see this has a lot of values that pass here. This is not really the number of parameters, because this is a convolution network, and the kernels use, the parameters are used, the same set of parameters over the whole image. But you can see these numbers 48, 128, and so on. These are the depth of the convolution layer, so the number of layers in each of these segments that produce different representations of the image. So basically, we are using here 48 different kernels applied to the input image that now will generate 48 feature maps for the image. So 48 representations of the image. Now here we have 128 representations of the image and so forth, and over the whole network until we reach the dense layers, the general multi-layer perceptron, and have the classification at the end. So in this case, they use two GPUs. They split the network into the two GPUs to train and use the two in parallel.
How do you choose the number of layers in the
That's trial and error. Yeah, that's basically the no free lunch problem. You cannot say use this number of layers and it will always work. It will work well in one data set and not in another. So you really have to experiment. However, we will also see that it's not really that bad, because you can train a network in one set of images, and then basically what we're looking at here is that all that this part is doing is generating good features for the classification. So this is basically feature extraction. And if you have similar images, then the features this will generate, even without additional training, will probably be good enough for classifying new images. So you just have to look at the end and adjust the end or change the end of the network. We're going to see an example of that, by the way. This is from 2015. This is another network. So these blocks are actually represent the convolution layers, and then there are pooling layers here. There are some in parallel and so on. So the architecture is a bit more complex. We have a total of around 100 blocks here. Each block is something like this, with lots of filters and thousands of values there. So you can start to get really very large networks. This one has only 6.67 top 5 error. This is the percentage of times it can put a correct image in the top 5. So a correct class in the top 5 classes it assigns to an image. Now I'm going to give you a different example, a bit stranger, but to show you the idea that this is not just about having one network and training and getting the results. You can do more sophisticated things with this. So this is for generating visual explanations. I'm going to show the result. This is something like this. We give the system the image of a bird, and it identifies the bird. This is a pine grosbeak, and then it says that it's because this bird has a red head and breast with a gray wing and a white wing. And so you can see that the explanation is a bit weird. It's not human written text, but this is generated by the system, learning from this kind of description. So this identifies this as a Kentucky warbler because it's a yellow bird with a black cheek patch and a black crown. And it tries to give an explanation, a justification of why that bird was identified. So this was done with two different networks. There is one convolution network which was trained for this USCD birds database, and it's used to generate the features for classifying the birds. And then there is these 5 sentences written by humans for each image. So this was using the Amazon Turk, which is a way of getting people to work on this kind of problems, where you pay each individual for the number of data he labels or submits and so forth. So they had, for each of the 12,000 images into these 200 categories, also had for each image 5 sentences written by humans describing the image. So this was used not only for the classification, this used a network that was already trained to recognize images. So basically it produces the set of features for the classifier. But then there are also 2 recurrent networks, these long short-term memory networks that work like this. So basically this is a rolled out representation, but the network is this, and the output goes back as the input. So the network is recurrent. And there are different operations, different input values that can lead to forgetting a value or adding a value or outputting 0 or 1, something like that. So basically the network is built in this way so that depending on previous states, the next state can change and can also receive other inputs. And they use 2 networks for this. One which started with the initial word and outputs an abstract state of the sentence, and this is fed into the other network that decides what are the probabilities for the next word, and then chooses the next word, which goes back to the first network that chooses the state, so that the 2 networks together will try to create sentences that make sense, that follow some kind of semantic regularity. And these are trained with a loss function that not only compares the words generated to the sentences that we have for each image, so this also uses the features from the image itself, and then also trained to try to maximize the words that are relevant for that class, so for that bird specifically. So basically it's not just trying to imitate the words that humans wrote, but those specific words that distinguish this bird from other birds, those elements in the description. So this uses a combination of a convolution network to create features from the image that then are fed into these recurrent networks. These recurrent networks were trained both to try to mimic the sentences humans wrote and to try to favor those words that make this bird different from the rest. And this is what then produces this kind of generates these expressions from the bird. So identifying the bird and then explaining what this bird has that other birds don't. Other applications of deep learning includes generating, for example, you have this is, I think the URL is something like this person does not exist or something like that. If you go there, you see an image of a person that was generated by a deep network. So this is not a real person, this was a photograph generated by the network, and if you refresh the page, you see another person and another, and it generates infinite persons. This is an NVIDIA test case where they trained a deep neural network with images of driving in town, and then the network generates images as if we were driving, and it even has persistence of objects and so on, but there is no model behind here, so the buildings are not modeled, or the roads and so on, just the images are being generated. So basically, if you try to drive again on the same street, it can be completely different, like a dream or something like that, but the images are generated and were learned from video images from real driving. So we can have, there are things that I cannot show here, like deep fakes and so on, where they're used for pornography, things like that, but there's lots of things that are, where deep networks are being used, not only for classifying and identifying, but also for generating data. So it's very easy to fake Barack Obama saying something with his own voice and the face moving, but it's something being said by someone else, and the network is just taking data from one set of images and outputting the other. Or things like you take a picture in a sunny day and then you change it to rain or a storm, something like that. You can do that with deep neural networks that are trained to make those changes to the image. So this is not just about identification, it's also about generating new data. And the basic idea here is that what the deep neural network is doing is changing the representation of the data. So depending on how you train it, you can get different representations, whether good features for classification or a different way of showing the data, or just making up new data from noise, which you can add. You can just represent noise in a way that looks like the face of someone, for example. So this is all for today. To sum up, the main message for this second part is this idea that we are stacking nonlinear transformations. So with a shallow learner, we need to do a huge nonlinear transformation to solve complex problems. But we are doing it blind. We are probably inserting there lots of noise that we don't want, and then we increase the problems with overfitting and so forth. With deep learning, we can do this more efficiently, more effectively by restricting the size of each layer and then combining the different nonlinear transformations. And the basic idea is that the network, you can think of a deep neural network, for example, a deep neural classifier, as one linear classifier at the end, which is the last neuron, and that's working on a set of features that was generated by the rest of the network. So 99% of the network tries to find the good features, and then the final guy just says yes or no. So, and you can use this for many other different things, with autoencoders just looking at those representations, for generating data, and so forth. So, for next week, if you're using your own laptops, you can install Anaconda. If you already did machine learning, you have Anaconda, so you just need to install TensorFlow. If you want to, you can install TensorFlow for GPU, but for this first part of the semester, that should not be needed. I test everything on CPU, and it just takes a few minutes to run, so you shouldn't need GPU acceleration. In any case, with TensorFlow and Anaconda, you can only use GPU acceleration if you have NVIDIA cards. And for reading, I would recommend this article by LeCun, Benjamin and Hinton. This is a review paper on deep learning from 2016 and talks about this kind of thing. Questions?
Can you please go back to the bird example?
Sure. Here?
No, the previous one, yeah. Why does use the recurrent neural net?
Because you need to generate these texts, and you generate one word at a time. And the word that comes next depends not only on the features of the image, because that is input into this network, but also the previous words on the sentence, because the sentence must be a chain of things with meaning. It cannot be independent. And actually, it's two recurrent neural networks. One is keeping track of this L value, they call it an L, but it's something abstract, which basically, based on the previous words, gives you an idea of what state you're in inside the sentence. And the other one takes that and the image data and decides what should be the next word. Okay?
And all the convolutional neural network is doing feature extraction.
Yes. The convolutional neural network was actually trained previously on a data set of bird images and is just extracting features from that. Ok? Até para a semana. Eu vou tentar, como é aprendizagem automática, vou tentar fazer os apontamentos, já tenho alguns, mas não prometo que seja todas as aulas, garanto que vou conseguir acompanhar. Mas pelo menos para esta já está quase acabado. Mas não há uma...
Não são reguladas. A teoria não encontra explicações de teste. Não temos